this is a typo. Well, not a typo, but an error. This should be P. Yeah, boy. I'll start over. Probably didn't need to start all the way over. Yeah, okay. We can do just restart on that. Right, we should shift these expressions a little bit over so that the assertion arrow doesn't offset, but too late for this one. I'll go ahead and simplify this step. we could do the blues instead. Since we've used reds for quantification, we can also use greens. Here, let's use P. 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 And then we can use the blues for sets. think I'll just call that there. Good enough. Good enough, even wholly adequate. Exercises give a counterexample to the following statement. So this is what I was talking about with the proof method, making clear what counterexamples we're looking for, what would constitute a counterexample. So the expression the domain of A is equal to the empty set gives us that not there exists a U such that the ordered pair TU is an element of A. Okay. But that's not the only kind of element there is. Right, so A is equal to the set containing A, or I don't know, 1, which is a way of gesturing towards the idea that it can't be an ordered pair unless we somehow insisted that numbers were ordered pairs. Now, what if I said relatedly, domain of A is equal to the empty set, and for all let me think here. For all B, if B is an element of A, then not there exists a C such that not there exists a C and there exists a D such that B is equal to the ordered pair. No, that's not what it would be. Routing. Rather, the domain of A is equal to the empty set, and for all B, should we do for all D, I guess? For all D, if D is an element of A, then there exists an S and there exists a T such that D is equal to the ordered pair ST. Exciting. Okay, sure. Well, that would be a contradiction, from which we can derive anything. Yeah. Well, no, that wouldn't be a contradiction, would it? Because now we're saying, right. For all E, not E is an element of the domain of A. These bracketing rules are getting more complicated by the day. Not E is an element of the domain of A, and for all D, if D is an element of A, then there exists an S and there exists a T such that D equals the ordered pair ST. Okay. Yeah, we have to get really convoluted here. We also have to get convoluted in a way that I'm not used to getting convoluted. I think we can narrow down the quantification though and just say that this would be interderivable with, if we distributed this through, after taking the conditional equivalence, I'm going to take some shortcuts here. E is an element of the domain of A, and not E is an element of A. That doesn't make sense. Let me think here. Yeah, that's another mistake. Okay, let's see. Because this is, yeah, this shouldn't be capital because this isn't a set, so this should rather be for all P not P is an element of the domain of A. And for all E, if E is an element of A, then there exists an S and there exists a T. We've got a D instead of an E. D equals the order pair is T. Okay. And then this would be for all P not there exists a Q such that the ordered pair PQ is an element of A. And for all D not E is an element of A. Let's say not D is an element of A, or there exists an S and there exists a T, such that D equals the order pair is T. I'm getting lost here. Hmm. what we're trying to get is that if we and on the expression E is an element of A and not there exists a M and an N such that E equals the ordered pair Mn, and we're going to get a contradiction out of that, ideally. Skipping this quantification to save room. So this is going to give us not the ordered pair PQ is an element of A, or D is an element of A. And I take this to simplify. If there exists an S and there exists a T such that D is equal to the ordered pair ST, and for all P and for all Q not the ordered pair PQ is an element of A, then not D is an element of A. Okay, but do I want to simplify that? Well, we could say if the ordered pair PQ is an element of A or D is an element of A, then there exists an S such that D equals the ordered pair ST and not the ordered pair PQ is an element of A. Take the conditional equivalence. Sure. And to make this, to simplify this a little bit, I think we can shed this. We're free to shed ands in the consequence, according to our homebrew set theory, such as it is. Alright, so now we want to say the ordered pair PQ is an element of A, or D is an element of A. Then there exists an S and there exists a T such that D is equal to the ordered pair ST. Okay, and now I'm going to say and blue where blue in this context is so this would be like an additional hypothesis, hence this color combination, this strange and irregularly used color combination. We don't carry around hypotheses, but this is the same color scheming that we used for this back here. No, not that. Back here. So we're going to say, I'm going to say E is an element of A. And not, there exists an M and there exists an N such that E is equal to the ordered pair MN. Okay. And now the idea is that if I give this expression, give this indigo, and we'll give this violet blue, and we'll give this violet. Alright, now indigo blue. And violet blue. Yields. That might be biconditional, but it doesn't matter for this purpose because it's going to be a contradiction either way. This will yield that there exists an S and there exists a T. Such that D is equal to the ordered pair ST. Okay. And let's confirm that real quick if I have. If I have P P or Q, then R, we may derive R, and P. Yeah, okay. We may derive R. Okay, that'll be our lemma here. So I have P or Q, then R and P, which is interderivable with the expression not P or Q or R and P, which is interderivable with the expression not P and not Q or R and P. Okay, which is interderivable with the expression P and not P and not Q or P and R. Now, this is plainly a contradiction. Okay. If and only if P and R, from which is forward derivable R. Okay. The significance of this being E is an element of A, and for all D, for all P, and for all Q, the ordered pair PQ is an element of A, or D is an element of A, then there exists an S and there exists a T such that D is equal to the ordered pair ST. Okay, so we will forward derive into the expression there exists an S and there exists a T such that D is equal to the ordered pair ST and not, I guess this would actually be E is equal to I'm not exactly sure about the syntax here, but I'm saying for all D, if D is an element of A, then D equals the order pair ST without the quantifiers. E is an element of A, therefore E is equal to the order pair ST. Seems reasonable to me. Not there exists an M and there exists an N such that E is equal to the ordered pair MN, which I take to be a contradiction, though we're skipping maybe a few steps. And the point of this proof was to show that we can place the restriction well, I mean, really what this shows is this is a proof by contradiction. Though interestingly, the way this is a proof by contradiction, if I knew how to structure a commentary on it, I think I'd make this point that this is what this use of contradiction here is different, I think, from this use of contradiction. Like, this is a step in our algebra. This is a simplification rule, a typographical rule, that P and not P is a contradiction and allows it allows however we handle contradictions in our algebra. Well, it's the justification for an algebraic operation. Okay, this, saying that we've proven something by deriving a contradiction, is different from taking an algebraic step. How it is different, I'm not exactly sure. Or what to make of that difference, I'm not exactly sure. Like, it wouldn't make sense to me to deny myself this algebra operation in my set theory, but I might strive to avoid producing proofs that relied on generating a contradiction. That would not itself be any kind of inconsistency, I think. Anyway. Which, if any, of the analogues of theorems 5, 6, and 7 hold for the operation field? All right, exercise 2. Okay, so domain of A, rather the field of A union B is equal to the field of A union the field, that's the domain, field of B. What is the definition of field? Let's see. So the field of A is equal to the domain of A union the range of A. That is definition 5. Okay. For all T, T is an element of the field of A union B is interderivable with the expression T is an element of the domain of A union B. Union. The range of A union B. Okay. Which is interderivable with the expression T is an element of the domain of A union B, or T is an element of the range of A union B. Okay, which is interderivable with the expression there exists an S such that the ordered pair, that should be U. There exists a U such that the ordered pair TU is an element of A union B, or there exists an S such that the ordered pair ST is an element of A union B. Okay. I'm beginning to wonder how anyone ever gets through a math book. I have done it, but we are not far into this book, and I've dumped hundreds of hours into it. Less than an hour per page. Less than a page per hour. It's like 3 or 4 hours per page, 5 hours per page, if I were to guess. Anyway. Okay. Okay, but this kind of step actually wasn't necessary, was it? I don't know. Let me think here. zoning out a little bit, one moment. I'm wondering if... Well, okay, so I'm wondering if this might be forward derivable, this next step, and if so, there should be a counterexample that arises from that forward derivability. So if I want to break this down, what I'd want to say is interderivable with the expression that T is an element of the domain of A, and T is an element of the domain, or T is an element of the domain of B, and T is an element of the range of A, or T is an element of the range of B. Okay, but then what are we doing with these U and S we had to quantify into existence? Okay, but I actually don't think that is... I don't think that's a required step down, because if when we say that think here. Well, yeah, because we could step back forward. I mean, if we proceed to saying, I'll put a question mark here, though that's not really one of our math symbols, is it? So here we'd be saying, let's see, there exists a U such that U is an element of the range of A, and T is an element of the domain of A, or U is an element of the range of B, and T is an element of the domain of B. Okay. Or there exists an S such that S is an element of domain of A, and T is an element of the range of A, or This is wrong. This should be an and. No, it should be or. Because the field expression itself is, yeah, okay, never mind. So, what I'm thinking here is that we could step down and say, shed and here, shed and here, shed S here, shed S here, and then we get T is an element of the domain of A, or T is an element of the domain of B. Or T is an element of the range of A. Or T is an element of the range of B, which is interderivable with the expression. T is an element of the domain of A union the domain of B. Or T is an element of... that's not how we would want to group that. T is an element of the domain of A, or T is an element of the range of A. Or T is an element of the domain of B. Or T is an element of the range of B. Okay. If and only if T is an element of the field of A, or T is an element of the field of B. Alright, so the question here is, did we have to step down on either of these two cases? And I think the answer is no, because if I start out by saying this actually doesn't answer my question, what I'm about to do, because we might feel obliged to step this down and nevertheless be able to derive back in the other direction, and then we get our equality not by direct interderivability, but by being able to choose a different routing going in either direction, as sometimes happens. We get the equality through that routing. So if I say T is an element of the field of A, or T is an element of the field of B, interderivable with the expression T is an element of the field of A. The domain of A or T is an element of the range of A. Or T is an element of the domain of B, or T is an element of the range of B. Alright. Which is interderivable with the expression there exists an S, there exists a U such that the ordered pair TU is an element of the domain of A, rather is an element of A. Or there exists an S such that the ordered pair ST is an element of A. Or dot dot dot, and I'll call that good enough because it gets us right back here. Or we were, so, okay. One way or the other, we get the interderivability. So, yeah, I'll call that. So 5, 6, and 7. So we will now do exercise 2, part B. So it's exercise 2A. The field of A intersection B is a subset of the field of A intersection the field of B. Okay. Is it true? For all T, T is an element of the field of A intersection B is interderivable with the expression that let's see. T is an element of the domain of A intersection B, or T is an element of the range of A intersection B, which is interderivable with the expression exists a U such that the ordered pair TU is an element of a intersection B. Okay. Or there exists an S such that the ordered pair ST is an element of A intersection B. Okay. Which is interderivable with the expression. The ordered pair TU is an element of A, and the ordered pair TU is an element of B. Not a good reason to drop our quantifiers. Okay, let's just do it with color. So I think probably we have to distribute this, and the reason we have to distribute this is that we have to get these two terms together and these two terms together. Though we will also get these two terms together if we distribute. Which is not ameliorated by, let's just suppose we accept that we had to step down, and yet nevertheless we can go in the other direction. A curious, unusual case. Now I say T is an element of the domain of A. Is an element of the domain of B, or T is an element of the range of A. Okay. So let's distribute in this fashion. Doesn't really matter how we do it. T is an element of the domain of A, or T T is an element of the range of A, and T is an element of the range of B. Okay, and T is an element of the domain of B, or T is an element of the range of A, and T is an element of the range of B. Okay. And then when we distribute those through, okay, and now the point is, well, these are all and associative, and we can just ditch the ones that we don't want. We have domain of A, range of A, domain of B, range of B. We'll ditch the terms from which we cannot derive a field expression. So, forward derivable T is an element of the domain of A union the range of which is interderivable with the expression that T is an element of the field of A, and rather, T is an element of the field of B, which is interderivable with the expression T is an element of the field of A intersection the field of B. Okay. Alright, now the last one. We're so few pages ahead of this position. We are disturbingly few pages ahead of this condition, or this position. Let's see. Oh, all the way back here on page 6, which was like 3 months ago, or 60, which was like 3 months ago, or whatever. Theorem 7. Okay. Now, in the past, making that observation, I would be feeling distraught. Now I'm feeling bemused. Example 2C. Alright, so the field of A minus the field of B is a subset of the field of A minus B. Okay. Sure, let's find out. Alright, so for all T, T is an element of the field of A minus the field of B. Is interderivable with the expression that T is an element of the field of A and not T is an element of the field of B, which is in turn interderivable. Yeah, which is in turn interderivable with the expression T. There exists. Oh yeah, okay. T is an element of the domain of A, or T is an element of the range of A. Okay, and not T is an element of the domain of B, or T is an element of the range of B. So conveniently here, I don't think we need to... I think we could just distribute through here. We don't need to take the intermediate step through ordered pair expressions, ordered pair terms. So without distributing the negation yet, actually that's probably not a good idea. Yeah, for that matter, it simplifies things to have this in and, because then I can and on to these internal expressions. Okay, so interderivable with t is an element of the domain of A, or t is an element of the range of A, and not t is an element of the domain of B, and not t is an element of the range of B. Okay, so now this will be the distributor. These will be the distributands. Sure. So we're going to have yeah, it looks like this is going to work out fine. So we're going to have not t is an element of the domain of B, and not t is an element of the range of B, and t is an element of the domain of A. Normally this term would go on the left. Well, or okay, so now I will shed this term, and I will shed this term. So forward derivable with t is an element of the domain of A, and not t is an element of the domain of B, or t is an element of the range of A, and not t is an element of the range of B. Okay. Which is interderivable with T is an element of the domain of A minus the domain of B. Or T is an element of the range of A minus the range of B. Okay. Now, is that the expression I would want to get out of the other side? For all P, P is an element of the field of A minus B. Is interderivable with the expression P is an element of the field of A minus B, or P is an element of, no, rather, the domain of A minus B. The range of A minus B. Let's see. Okay, so this would be if and only if there exists an N, no, there exists a Q, such that the ordered pair PQ is an element of A minus B. Or there exists an N such that the ordered pair in P is an element of A minus B. Okay, which is interderivable with the expression. Now we're probably going to need that on 2 rows, 2 lines, so we'll go to the next page. Which is interderivable with the expression. There's this Q such that the ordered pair PQ is an element of A and not which in fact brings us back to this expression. So yes. So we'll call that there. All right. And that is exercise 2 completed, because we have equality with where we left off. Is equality, right? Yep. And we had to step down the biconditional here when we shed these two terms. Okay. Next exercise. Prove that the Cartesian product of two sets is a relation. So that'll be A by B is a relation. Alright. That's exercise 3. Okay. Wrong color. This is fixable. Alright, so now A is a relation is defined to be interderivable with the expression for all x. X is an element of A. Fix that for all S. For all S. Actually, just stick with T. T is a nice one because you have letters on both sides that you can dig into. S is also a good one. Anyway, T is an element of A, then there exists a U and there exists a V, such that T is equal to the ordered pair UV. Okay. And now, what about Cartesian product? A AB is equal to the set containing as elements ordered pairs of the form ST such that S is an element of A and T is an element of B. Alright. Let's see. The ordered pair AB is a relation is interderivable with the expression I shouldn't have used T here. We can do PQ here. If and only, or is interderivable with the expression for all T T is an element of this is going to get a little bit unruly here, but whatever. T is an element of the set containing as elements. Actually, yeah, this should be D, because it's a set. Capital letter at any rate, doesn't have to be D in particular, but for all capital D, D is an element of the ordered pair containing, rather, D is an element of the set containing as elements ordered pairs of the form PQ such that the ordered, such that P is an element of A and Q is an element of B. Then there exists a U, and there exists a V such that D rather in this case, D is equal to the ordered pair UV. So actually the author didn't stick to that convention up here, choosing T to represent an ordered pair, or whatever. So the ordered pair A by B is a relation if and only if, yeah, we skipped a little bit of a step. Actually, we have enough room, probably. Okay, the order A by B is a relation if and only if for all D is an element of A by B, then there exists an U and there exists a V such that D equals the ordered pair UV, which is interderivable with the expression for all D is an element of the set containing as elements the ordered pairs of the form PQ such that P is an element of A and Q is an element of B, then there exists an E and there exists a U and there exists a V such that D is equal to the ordered pair UV. Which is true. Turns into a tautology. I have to remember exactly what we do here. Don't need the quantifier. Let's see. If and only if there exists in M and there exists in such that D is equal to the ordered pair Mn, and M is an element of A, and N is an element of B. Then there exists a U and there exists a V such that D is equal to the ordered pair UV. Okay, so I guess the point is that we shed. Yeah, I'm trying to think whether stepping down our expression matters here. Yeah, we can always give it give it a color. Alright, so this is forward derivable. Which is interderivable with the expression not. There exists a U and there exists rather an M and an N. Such that D is equal to the ordered pair M N. Or exists a U and there exists a V such that D is equal to the ordered pair UV. Okay. Which I will take to be a tautology. without further ado. Normally, yeah, we could indicate that by underlining the or. Alright. Okay. Yeah, that would be a good convention. Let me come back here. This is a little bit out of order, but whatever. Alright. Okay, I will take a break. We're back. Okay. Exercise 3 complete. Prove Theorem 3 done. I proved all of the theorems on the way here. Under what conditions does the domain of A by B equal A? Okay, so this is exercise 5. Alrighty. Let's see. So, for all t, t is an element of the domain of A by B is interderivable with the expression there exists a U such that the ordered pair TU is an element of A by B. Okay. Which is interderivable with the expression that the ordered pair TU is an element of the set containing as elements ordered pairs of the form PQ such that P is an element of A and Q is an element of B. Okay. So there exists an R, no, there exists a, yeah, okay, R and S, interderivable with the expression, there exists an R and there exists an S, such that the ordered pair TU is equal to the ordered pair RS. And R is an element of A, and S is an element of B. Okay, which we retain interderivability when we say if and only if T is an element of A U is an element of B. Okay. Though interestingly, we have to step this down. Then T is an element of A. Which is, in fact, interderivable with the expression, or rather, this derivability sequence obtains when the domain of A by B is a subset of A. Okay, which let's see. So the counterexample is that B is equal to the empty set. Which is suggested. I mean, you can figure it out without too much thinking, maybe. But it's suggested by having to remove this term, interestingly. So we're keeping a keen eye on when the proofs that we undertake give us pointers towards, give us an idea of what direction we're going in. And in this case, we get this step down. We had to remove there exists a U such that U is an element of B. Okay, so now we rarely do examples, but if A is equal to the set containing its elements 1, 2, and B is equal to the empty set, then the domain, well then A by B is equal to the empty set, and the domain of A by B is equal to the empty set. What I actually wanted to do here was and on a term. Yeah, well, I mean, if we had started with for all T T is an element of A, and there exists a U. such that U is an element of B, then we have our interderivability. Okay. Exercise 6. Out of 29, though many of them are proving theorems that we've already proven. Yeah. Exercise 6. The field of A by B is equal to A union B. So I assume this will have a related yield a related observation. Okay, and what is that? Well, let's see. For all t, t is an element of the field of A by B is interderivable with the expression that t is an element of the domain of A by B, or t is an element of the range of A by B. Okay. Which is interderivable with the expression there exists a U such that the ordered pair TU is an element of A by B. Don't need that bracket. Also, I'm going to get a blister here, remarkably. Unbelievable. Which might mean I should call it after this exercise. We can look at software foundations for a little bit. 30 minutes or so. Let's see. Or there exists an S such that the ordered pair ST is an element of A by B. Alright, so this one gets kind of horrible. So horrible, in fact, that maybe we don't want to do maybe I don't want to risk the blister. Yeah, well, we've written, like, we've covered a lot of ground in terms of pages in this notebook, not in terms of distance in the book, but So this will be there exists a U, there exists a V, and there exists a W such that the ordered pair TU is equal to the ordered pair VW, and V is an element of A, and W is an element of B. Or there exists an S and there exists a P and there exists a Q such that the ordered pair ST is not an element of but rather equal to the ordered pair PQ. P is an element of A, and Q is an element of B. Okay, which we take to be interderivable with there exists a U such that T is an element of A and U is an element of B. Or there exists an S such that S is an element of A and T is an element of B. Okay. And now here again we need to step down. If we are going to meet the requirements of the proof. Because we're going to be saying T is an element of A, or rather, T is an element of B. And we stepped down due to dropping this and term and dropping this and term. Okay. So it's interesting here if we start with saying T is an element of A. So for all T T is an element of A, and there exists such that U is an element of B, then we can go in the other direction. Where we say T is an element of A and there exists a U such that U is an element of B, or there exists an S such that S is an element of A and T is an element of B. And then we can go all the way back in the other direction. So we don't need both. We don't need both there exists an S such that S is an element of A and there exists a U such that U is an element of B, because we can well, we already know we can get back from the original expression. So it doesn't bother us if we have to step this down, because then we would get, let's see, dot, dot, dot. We could derivability in both directions. An interesting case, contrasting with earlier, where, well, yeah, I mean, we could directly get the interderivability instead of, we could directly get the interderivability if we said, for all T, T is an element of A and there exists a U such that U is an element of B and there exists an S such that S is an element of A, then that would be interderivable dot dot dot. But the only thing we've won by doing that is not needing to specify that you have to prove in both directions. Prove forward derivability in both directions. Okay. That was exercise 6. Prove theorems 6 and 7. Ah, we did that earlier. Our 3 hours or whatever covered one line of this page. Yeah, well. This book is so slow. So slow. Well, I mean, the book doesn't say prove every theorem in the book. But on the other hand, I have a hard time understanding what the point of telling me all these theorems is. Like, I'm not going to memorize all of these theorems. I could use it as a reference manual, I guess. We're earning the right to use this as a reference manual. All right. Yeah, I'm gonna get a blister if I keep going. So, let's look at what I've been doing in Raqqa. We've been proving theorems. Many theorems. I also got a memory leak on one of these files earlier. The author wants us to continue with some coding, writing functions. I don't want to do that at the moment. One second. Alright, let me get pull the book up. So this is part of our hybrid mathematics and computer science education. That I am giving myself. However, I am not an accredited institution, consequently, this is worthless, but let's see. So we've mostly completed proof by induction, except that we still have these coding exercises down here at the end. However, I also skipped the coding exercises in the last chapter, and these reference those coding exercises, so I'm going to go back tomorrow and do all of them. Or get started anyway. Working with structured data. Yeah, I don't know, I guess it'd be kind of awkward to get this switch in. I don't really want to stop studying at the moment. I do want to put in the extra 30 minutes, but 25 minutes. I could put a band-aid on my thumb. Yeah, I guess I'll call it. It's kind of, since I'm uploading these to YouTube, it'd be kind of odd to switch over to this. I'll consider looking at this on my own time. I will return. In all likelihood, tomorrow. I guess I can check. Nope. Alright.